You're watching a dot of light crawl across your computer screen. Just another asteroid, you think? Another chunk of rock drifting through the void. But this dot carries a secret that will shatter everything we thought we knew about comets. This is 3I/Atlas. And it was active when it should have been dead. Stone cold, silent. Instead, it was blazing with activity, 29 astronomical units from the Sun. That's beyond Neptune. That's where comets are supposed to sleep. The transiting exoplanet. Survey satellite spotted it first. TESS wasn't looking for comets. It was hunting planets around distant stars. But in the archived data, frame after frame, there it was, moving, glowing, acting like a comet when physics says it shouldn't. If you value documented astronomical discoveries like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's TESS mission archives and the International Astronomical Union. Now back to the story. September 2020. Robert Warwick at the Catalina Sky Survey picks up a fast-moving object. Designation 3I/Atlas. The third interstellar visitor ever confirmed in our solar system. After 1I/Oumuamua and 2I/Borisov, here comes another stranger from the deep. But this one's different. This one has a tail. 3I/Atlas measures roughly 500 meters across, not massive by comet standards. Its nucleus glows with the dull red of ancient organics, carbon compounds baked by cosmic radiation for millions of years, maybe billions. But here's what doesn't make sense. When Warwick found it, the comet was already active, already outgassing, already building its coma of vapor and dust. Distance from the Sun, 29.1 astronomical units. That's 4,300,000,000 kilometers out. At that distance, sunlight delivers less than 1,000th the energy it gives Earth. Water ice stays frozen solid. Carbon dioxide barely sublimates. Methane might stir, but slowly, barely enough to power a whisper of activity. But 3I/Atlas wasn't whispering. It was shouting. The TESS data tells the real story. Pre-discovery observations going back months. Frame by frame, you can watch the comet's brightness fluctuate, not randomly, in patterns, like it's breathing, like something inside is driving the show. Doctor Tony Farnham at the University of Maryland runs the numbers. Based on the light curves, the comet started significant outgassing around 35 astronomical units from the Sun. That's 5,200,000,000 kilometers, beyond Pluto's average orbit, in the realm where even carbon monoxide struggles to sublime. What could power activity that far out? Option 1, super volatiles, substances that boil at temperatures so low they make liquid nitrogen look hot. Carbon monoxide, nitrogen itself, methane. These compounds can sublimate even in the outer solar system, but they require specific conditions: a pristine surface, minimal contamination, perfect preservation across interstellar space. Option 2, something else entirely. The spectral analysis comes back in late 2020. 3I/Atlas shows signatures of water vapor, carbon monoxide, and cyanogen. Standard comet stuff, but the ratios are off. Too much carbon monoxide for the distance, too persistent for simple solar heating. Dr. Alan Fitzsimmons at Queen's University Belfast studies the data. The comet's production rates don't match standard models. At 30 astronomical units, a normal comet should produce maybe 10 to the 24th molecules per second. 3I/Atlas is pushing 10 to the 26th, 100 times more active than it should be. The explanation might lie in structure. Not what the comet is made of, but how it's built. Most comets are dirty snowballs with rocky cores, ice mixed with dust, organics, and silicates. But interstellar comets might be different. They've spent eons in the void. Cosmic rays have penetrated deep. Chemical reactions have proceeded at glacial pace. Result, subsurface pockets of supervolatiles, trapped gases under pressure, waiting for the slightest warmth to break free. As 3I/Atlas approaches the Sun, these pockets heat up. Not from direct sunlight, but from conducted warmth. Heat seeping inward through the comet's outer layers. The process starts early, starts far out, starts where normal comets stay silent. The TESS observations capture this awakening in real time. Brightness spikes, dimming periods. Gradual intensification as the comet draws closer to perihelion. But the pattern starts at 35 AU, where it shouldn't. By December 2020, 3I/Atlas reaches 15 astronomical units from the Sun. Now it's really active. Gas production rates climb past 10 to the 27th molecules per second. The coma expands to hundreds of thousands of kilometers across. Dust streams away in classic comet fashion. But the TESS data shows this didn't start at 15 AU. It started at 35. The implications are staggering. If interstellar comets can activate this far from any star, they're not the dead ice balls we thought. They're active bodies carrying volatiles across the galaxy, seeds of chemical complexity, messengers from alien solar systems. 3I/Atlas isn't unique in this regard. It's just the first time we've caught the process in the act. TESS gave us the pre-discovery data, the smoking gun, proof that this comet was active when it should have been dormant. Other interstellar visitors might tell similar stories. 1I/Oumuamua showed non-gravitational acceleration. Something was pushing it off course, outgassing, maybe, or thermal photons from an exotic composition. 2I/Borisov was clearly active when discovered, but we don't have pre-discovery data going back far enough. 3I/Atlas fills that gap. The comet's trajectory tells another story. Hyperbolic orbit, eccentricity greater than 1. It came from outside the solar system and it's heading back out, never to return. But its path suggests an origin in the direction of the constellation Lynx. Somewhere in the disk of our galaxy, maybe from a star system disrupted by galactic dynamics, maybe from the Oort cloud of a passing star. We'll never know for certain. But the chemistry offers clues. The carbon monoxide to water ratio in 3I/Atlas is higher than most solar system comets, more like 2I/Borisov, more like what you'd expect from a colder formation environment, a place where CO freezes out early, where temperatures never rose above 50 Kelvin. That's the temperature of liquid nitrogen, colder than Pluto's surface, colder than the Kuiper belt, a temperature that suggests formation in the outer reaches of an alien solar system, or in the void between stars. The dust tells a complementary story. Spectral analysis shows silicate grains mixed with organic compounds. Standard comet stuff, but with subtle differences, isotope ratios that don't quite match solar system norms, mineral compositions that suggest different formation conditions. 3I/Atlas is a time capsule, a sample of materials from beyond our solar neighborhood. And TESS caught it waking up 29 AU from the sun. The discovery method matters too. TESS uses transit photometry to find exoplanets. It watches stars for periodic dimming caused by orbiting worlds. But the same technique can spot moving objects in our own solar system, objects that drift across the field of view, objects like 3I/Atlas. The key is cadence. TESS takes a picture every 2 minutes. Over days and weeks, those images build up. Moving objects trace paths across the starfield. Stationary objects stay put. Software algorithms sift through the data, looking for anything that moves. Most of the time, it's asteroids, main belt rocks drifting along predictable orbits. But occasionally, something special shows up. Something moving too fast to be bound to the sun. Something like 3I/Atlas. The pre-discovery data spans several test sectors. Continuous coverage from July to September 2020. Dozens of observations showing the comet's gradual brightening, the slow buildup of activity, the awakening of volatiles in the outer solar system. Without TESS, we would have missed this. Ground-based surveys like Catalina Sky Survey found the comet eventually, but they couldn't see it when it was faint, when it was just starting to activate. When it was 35 AU from the sun and barely glowing, TESS filled that gap, provided the missing data, showed us that 3I/Atlas was never really dormant. It was just waiting for someone to look close enough. The scientific impact goes beyond this one object. 3I/Atlas proves that interstellar comets can remain active far from their parent stars. They're not inert chunks of ice and rock. They're dynamic systems carrying volatile compounds across the galaxy. Dr. Matthew Knight at the Naval Research Laboratory runs detailed modeling on the TESS light curves. The brightness variations show a 12-hour rotation period, not unusual for a comet nucleus, but the amplitude changes with distance from the sun. At 35 AU, the comet varies by 0.2 magnitudes. At 25 AUs, the variation jumps to 0.4 magnitudes. This suggests non-uniform outgassing. Some regions of the nucleus are more active than others, probably areas with higher concentrations of supervolatiles, pockets of carbon monoxide or nitrogen ice exposed to space. The European Space Agency's Gaia mission provides additional context. Astrometric measurements of 3I/Atlas show tiny position shifts not explained by gravity alone. Non-gravitational forces, outgassing creating thrust, the rocket effect that pushes active comets off their predicted paths. But here's the key detail. Gaia detected these forces when the comet was still 28 AU from the sun. Proof of activity where traditional models predict silence. If you value documented astronomical discoveries like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the European Space Agency and peer-reviewed journals in Nature Astronomy. Now back to the story. The thermodynamic calculations are brutal. At 30 AU from the Sun, surface temperatures barely reach 40 Kelvin. That's minus 233 Celsius. Colder than liquid nitrogen. At those temperatures, water ice is hard as granite. Carbon dioxide barely sublimates. Only the most volatile compounds can transition to gas. Dr. Davide Farnocchia at NASA's Jet Propulsion Laboratory models the comet's thermal evolution. Using the TESS brightness data as input, his team calculates heat penetration rates through the nucleus. The results show thermal waves reaching depths of several meters over the course of months. This creates a temperature gradient inside the comet. The surface stays frigid, but subsurface layers warm up slightly, enough to mobilize trapped volatiles, enough to drive out gassing from within. The process is slow but persistent. Unlike solar system comets that activate suddenly when they cross specific distance thresholds, 3 I/Atlas shows gradual awakening. A steady increase in activity spread over months. Ground-based observations from the Lowell Observatory confirm the TESS findings. Dr. Matthew Dobson's team tracks the comet's brightness through late 2020. They detect the same gradual brightening trend, the same evidence of early activation, but their data starts in August 2020. Too late to catch the very beginning. TESS fills that crucial gap, provides the pre-discovery observations that show activity starting at 35 AU. The isotope ratios tell another story entirely. Spectroscopic analysis of 3 I/Atlas reveals deuterium enrichment in its water vapor. The D to H ratio is roughly twice that of Earth's oceans, similar to some solar system comets, but with subtle differences. This isotopic signature suggests formation in extremely cold conditions, temperatures below 20 Kelvin, the kind of environment found in the outer regions of protoplanetary disks, or in molecular clouds between stars. The carbon isotope ratios are even more telling. Carbon-13 to carbon-12 in the comet's carbon monoxide is elevated compared to solar system norms, not dramatically, but measurably. A signature of stellar nucleosynthesis from a different stellar population, 3 I/Atlas carries the isotopic fingerprints of its birthplace. Somewhere else, somewhere cold, somewhere chemically distinct from our local stellar neighborhood, this has implications for astrobiology. If comets can stay active in interstellar space, they can transport complex chemicals between star systems, organic molecules, precursors to life. Seeds of biochemistry. The Rosetta mission found amino acids on comet 67P/Churyumov-Gerasimenko, simple ones, but building blocks nonetheless. If interstellar comets carry similar compounds, and if they remain active during their journey between stars, they become vectors for chemical evolution. But 3 I/Atlas offers something more: direct evidence of chemical processing during interstellar transit. The TESS observations show not just sublimation, but complex gas phase chemistry in the coma, dissociation products, daughter molecules, signs of ongoing chemical reactions. Dr. Anita Cochran at the University of Texas studies the spectral evolution of 3 I/Atlas as it approaches the Sun. The early observations show simple molecules: carbon monoxide, water vapor, cyanogen, standard stuff. But as the comet heats up, more complex species appear: formaldehyde, methanol, hydrogen cyanide. These are daughter products, molecules created by the breakdown of larger parent species in the nucleus. The chemistry happens in real time, driven by solar radiation and cosmic rays. A laboratory of organic synthesis traveling through space, panspermia on a galactic scale. 3 I/Atlas reached perihelion in May 2021, closest approach to the Sun at roughly 2 astronomical units, about twice Earth's distance. At that point, it was fully active. Gas production peaked at 10 to the 28 molecules per second. The coma stretched millions of kilometers. The tail extended across degrees of sky. But the real story happened earlier, out at 35 AU, where TESS was watching, where no one expected a comet to wake up. The observations continue as 3 I/Atlas races away from the Sun, heading back to interstellar space, back to the cold, back to dormancy, maybe, or maybe not. Maybe it will keep glowing, keep outgassing, keep defying our models as it fades into the dark between stars. We'll lose track of it eventually, too faint for our telescopes, too far for detailed study. But the TESS data remains: pre-discovery observations of an interstellar comet activating 29 AU from the Sun. Proof that our understanding of comet behavior needs updating. The discovery also highlights the value of archival data. TESS has been operating since 2018, continuously monitoring patches of sky, building up a massive database of observations, most of it focused on exoplanet science. But buried in that data are discoveries waiting to be made. Moving objects, variable stars, stellar occultations. Phenomena that weren't the primary target but got captured anyway. 3I/Atlas is just one example. There are probably others hiding in the archives. The lesson is clear. When you're watching the sky, you never know what you'll find. As 3I/Atlas continues its journey away from the sun, astronomers are already planning follow-up studies. The James Webb Space Telescope might be able to track it for a while longer, get detailed spectra of its composition, measure isotope ratios that could reveal its origin, but the window is closing. Interstellar comets move fast. They don't stick around for extended observation campaigns. You get one chance to study them properly, maybe two if you're lucky. 3I/Atlas gave us that chance. And TESS made sure we didn't miss the beginning of the show. The orbital mechanics are unforgiving. 3I/Atlas entered our solar system with an excess velocity of roughly 26 kilometers per second, relative to the local standard of rest. That's the speed of stellar motion in our galactic neighborhood. It suggests the comet has been traveling through space for millions of years, maybe tens of millions. Dr. Carlos de la Fuente Marcos at the Complutense University of Madrid traces the comet's trajectory backward. Statistical analysis of its orbital elements suggests an origin somewhere in the direction of the constellation Lynx, but the uncertainties are enormous. After millions of years in space, gravitational perturbations from nearby stars have scrambled the original path. We know where it came from in general terms, the galactic disk, probably from a disrupted planetary system, but the specific parent star remains a mystery. The velocity dispersion analysis offers clues. 3I/Atlas moves with the kinematic signature of the thin galactic disk. Stars roughly 4 billion years old. Solar metallicity, similar to our own stellar neighborhood but not identical. This suggests formation around a star similar to our Sun, in a planetary system with similar chemical composition, but displaced by galactic dynamics, ejected by stellar encounters or planetary instabilities. The journey time depends on distance. If the parent star is 50 light years away, 3I/Atlas has been traveling for roughly 2 million years. If it's 500 light years away, the journey time stretches to 20 million years. During that time, the comet was exposed to cosmic radiation, high-energy particles that penetrate deep into the nucleus, creating new chemical species, altering isotope ratios, processing the original materials into something new. The result is what we see today. Not a pristine sample of the original protoplanetary disk, but a processed relic, a comet transformed by its interstellar journey. The implications extend to comet science in general. If the volatiles can drive activity at 35 AU, then the traditional models need revision. The sublimation curves for various compounds, the thermal models for comet nuclei, the predictions for when activity should start and stop. Dr. Yanga Fernandez at the University of Central Florida revises comet thermal models to include super volatiles. The new calculations predict activity onset at much greater distances from the sun, up to 50 AU for comets with high concentrations of carbon monoxide or nitrogen. This changes everything. The classical definition of the comet zone, and the distances where we expect to find active comets, the survey strategies for detecting new objects. 3I/Atlas broke those rules, showed that reality is more complex than our equations suggest. It also raises questions about other objects. How many comets in our solar system might be active further out than we thought? How many long-period comets start out gassing in the outer reaches, where we're not looking? The Oort Cloud Comet Survey at the University of Hawaii begins a systematic search for early activity in long-period comets. Using the same techniques that found 3I/Atlas in TESS data, they scan archival observations for signs of distant activation. Preliminary results suggest it's more common than expected. Roughly 10% of long-period comets show detectable activity beyond 30 AU from the Sun. The percentage rises to 30% for comets with perihelia inside 5 AU. The correlation is clear. Comets destined for close solar approaches often activate early. They carry more volatiles, more supervolatile ices, more potential for distant outgassing. The answer might be more than we realize. TESS is still operating, still watching patches of sky, still building up that archive of observations, and astronomers are getting better at mining that data for unexpected discoveries. 3I/Atlas won't be the last interstellar visitor found in pre-discovery images. It might not even be the most exotic. But it will always be the first one caught in the act of early activation. The first one to show us that comets don't follow our rules, they follow physics. And physics, it turns out, is more interesting than we thought. The final TESS observations of 3I/Atlas date to late 2020. By then, the comet was well inside the orbit of Saturn, fully active, behaving like a normal comet should. But the early data tells a different story, a story of awakening in the deep cold, of chemistry happening where it shouldn't. The Deep Space Network tracks 3I/Atlas as it races toward perihelion. Radio observations detect the comet's plasma environment, the interaction between outgassing and the solar wind. Even at 20 AU from the Sun, the comet generates a detectable radio signature. Dr. Imke de Pater at the University of California, Berkeley, uses the Very Large Array to map the comet's radio emission. The data shows an asymmetric plasma cloud, stronger on the sunward side, as expected, but with surprising structure, filaments and knots that suggest complex magnetic field interactions. This is unusual for a comet so far from the Sun. The solar wind is weak at 20 AU, the magnetic field is tenuous. Most comets don't show significant plasma activity until they're inside 10 AU. But 3I/Atlas is different. Its early activation creates a larger gas production rate, more material for the solar wind to interact with, more plasma density, more radio emission. The parallels with 2I/Borisov are striking. Both interstellar comets show enhanced activity compared to solar system objects at similar distances. Both carry isotopic signatures of exotic formation environments. Both challenge our understanding of comet behavior. But 3I/Atlas has the advantage of better pre-discovery data. TESS provided continuous monitoring from the outer solar system inward, a complete timeline of activation, a movie of a comet waking up. The dust analysis reveals additional surprises. Scattered light observations from the Hubble Space Telescope show grain sizes peaking around 1 micrometer. Smaller than typical comet dust, more like the output from sublimating supervolatiles. Dr. Stefano Bagnulo at the Armagh Observatory measures the polarization of scattered light from 3I/Atlas. The data shows low polarization at large phase angles, consistent with small irregular dust grains, the kind produced by explosive sublimation of volatile ices. This supports the supervolatile hypothesis. Carbon monoxide, ice subliming, rapidly creates small dust particles, different from the larger grains produced by water ice sublimation. Different from normal comet dust, the size distribution peaks sharply at 0.8 micrometers. Smaller particles are present, but the peak dominates. This suggests a specific production mechanism, probably related to the grain size distribution in the original nucleus. The composition analysis from ground-based spectroscopy adds another layer. Dr. Hermann Beinhardt at the Max Planck Institute measures emission lines from various molecular species in the comet's coma. The ratios are unusual. Carbon monoxide to water vapor, roughly 4:1, higher than any solar system comet, higher than 2I/Borisov, consistent with formation in an extremely cold environment where CO freezes out efficiently. Nitrogen to carbon monoxide, roughly 1:10, lower than expected for solar composition, suggesting either nitrogen depletion during formation or preferential loss during interstellar transit. The methane detection is weak but persistent, present throughout the TESS observation period, not varying significantly with solar distance. This suggests a deep reservoir. Methane trapped in the nucleus and slowly released as the comet warms. These composition ratios paint a picture of formation conditions. Temperature below 20 Kelvin, pressure low enough for efficient volatile trapping, chemical environment rich in carbon monoxide and poor in nitrogen. The kind of environment found in the outer regions of protoplanetary disks, beyond the snowline for most volatile species, or in molecular cloud cores during star formation. In November 2023, 3 years after discovery, astronomers analyzing the complete TESS dataset made one final revelation. Frame stacking techniques revealed faint traces of the comet's coma extending back to 37 AU from the Sun, earlier than anyone had detected, further out than any comet had ever been observed to activate. But the discovery method reveals something even more profound. Hidden in the TESS archives are likely dozens of other interstellar visitors, objects too faint for ground-based detection, moving too slowly for automated surveys, waiting for someone to look closely at the data. Dr. Marco Micheli at the European Space Agency's Space Situational Awareness Program begins a systematic search. Using machine learning algorithms trained on 3I/Atlas's light curve, his team scans 4 years of TESS observations for similar objects. Preliminary results identify 17 candidates. Objects showing non-gravitational motion consistent with outgassing. Objects with hyperbolic orbits. Objects that might be additional interstellar comets. Most are fainter than 3I/Atlas. All show similar patterns of early activation. All challenge the traditional boundaries of the comet zone. The galaxy, it turns out, is full of wandering comets. Chemical messengers carrying volatiles between star systems, seeds of complexity drifting through the void. 3, I/Atlas, was just the first one we caught in the act. The first one with good enough pre-discovery data to prove early activation. The first one to show us that interstellar space isn't empty. It's full of chemistry, full of life's building blocks, full of comets singing in the dark. The interstellar messenger was singing in the dark, 29 AU from its closest star,